So here's the preferred alternative as we talked a little bit about earlier tonight, drilling two 12-foot orifices partially through the dam to the downstream at approximately the original stream bed elevation, leaving in these plugs of concrete, and then charge the holes into these plugs with explosives that during that storm, then the concrete would be evacuated and the sediment from behind the dam would move downstream in that 3 to 4 year storm. And here's what it looks like graphically. So you see the dam down at the bottom with those two red dots. That represents the holes in that little exhibit here on the left that would then be drilled to accept explosives. There is another element of this alternative that if the State Division of Safety of Dams, which is a regulatory agency that regulates large dams, if they cannot accept this idea of evacuating through explosive, then we may need to install gates either upstream or downstream of the dam in such a way that that then instead of using explosive, the gates would be essentially opened during that storm event. So, boring, yeah. Blow it, yeah. So the 65% design plan grant was that grant that started in 2017. We have a number of different items that we're doing: field investigations, structural evaluation, sediment hydraulic analysis. We need to look at how predictable storms are. I'm sure, as all of you know, when you look at a forecast, it looks like it's going to rain heavy, and then the next day the storm is gone. And so we need to know that when we decide to charge those holes with explosives, that the storm is coming and that the sediment will evacuate. We're also reevaluating the downstream project components that the Corps had in their project to make sure that we have the right mix, not too much, but just enough, sort of to right size those project elements. Because as I was talking to a lady in the audience during the break, all these project components downstream of the dam just makes the project more expensive and will take it longer to implement. So we're reevaluating those project components right now. We're also reevaluating the real estate plan. So in a nutshell, the sediment in the river is going to come up, and the water is going to be higher after the dam is removed than it is now. And so we're looking at infrastructure improvements where we have big communities. We're looking at where we have single structures in the floodplain, looking at potentially trying to acquire those homes or structures, and then where we don't have structures in the floodplain, we'll be looking at what appropriate measures there are to mitigate additional risk, and that's what the real estate plan and the reevaluation of downstream project components are. We're also looking at short and long-term water supply mitigation elements. So the Robles diversion will receive somewhere 2.5 times more sediment after the dam is removed than it does now. That's the coarse gravels and cobbles that is being currently trapped behind the dam. So we're looking at what improvements could be needed. As many of you know, since Thomas Fire, Casitas has been challenged to divert water in entering events because of all the sediment from the fire event, and so it's not the same, but there are going to be some similar aspects to the dam removal in the sense that there'll be sediment that they have not have to accommodate previously. We're also looking at short-term water supply impacts. So we have Ventura River Water District, Miners Oaks Water District. That 4 to 6% at Casitas that I mentioned that would be lost in that one storm event that couldn't be diverted, and then the city of Ventura all have concerns about the fine sediment flushing out of the reservoir. So we're going to be looking in the next couple of months at what things that we can do to offset or to mitigate those impacts from that sediment flushing on their water supply operation. Of course, we're also looking at the dam removal, and Brian will talk a little bit about that. But that obviously is one of the main components of this project is removing the dam. We also are looking at Camino Ciel bridge replacement. We have a consultant working on that, and I'll mention that very briefly tonight, as well as we're looking at 3 levees. 2 of them exist, one at Casilla Springs, one at Live Oak Acres, one that would be new at Miners Oaks. And then also updating the CEQA and developing a permitting plan on what permits will be needed and when we'll need to get them for the project. And then lastly, which we haven't hired a consultant yet to do, is an independent technical review of the project. And that'll be done probably sometime later this summer or fall to look at all the work that's been done to date and to get some nationally recognized experts to look at what we're doing, to validate or to critique what we've been doing. So here's a general schedule of the project, that 65% design planning study project, this CDFW $3.3 million grant. We're right about in the middle of the project. We've done a lot of work, which Brian and I will describe in a moment, but there's still quite a bit of work to do. This grant will run all the way till the fall of 2021. And so, as Hans indicated, or David indicated, we're working really hard to position ourselves to have that final design funding in place that we can pick up right as we're leaving off. And in some cases, like the levees and the dam, we think we're going to be ready to move into final design even quicker than the fall of 2021. So we're working toward lining up that money as well. So with that, I'm going to turn over to Brian Pearson from AECOM, and he'll talk about the work that AECOM and Stillwater are doing, and then I'll finish it up with some of the other contracts that we're working on.
What I'd like to share with you over the next several slides is really the science and the engineering in support of the dam removal alternative concept that Peter and others have described here tonight. That is really effectively dealing with the orifices through the concrete dam, the behavior of the dam under loading conditions, including static and dynamic loading. We'll talk about that in a little bit. And then the science of moving that sediment through the dam. My wife broke the news to me a while back that not everyone shares my enthusiasm for the compressive strength of concrete or the relative density of cohesionless soils. And as much of a disappointment as that was, I'm going to try to keep that in mind over the next minute. So we won't get into the technical minutia. A little louder, okay. Everybody's hearing me okay now? So the geotechnical boring piece, we needed to understand and be able to characterize the sediment so we knew how they would mobilize from the reservoir, through the dam, and down into the river course, stream and river course below. So the way you do that is you drill into the reservoir sediment and do in situ tests, that's tests on the sediment while it's in place, and then also take samples of the sediment for laboratory testing. So this is a barge that does that work. It's about 27,000 pounds. It's equipped with a drill right here in the center that drills down through the center of the barge and into the sediment. Over to the right is a map of the reservoir. This is the dam right here. Each of these black rectangles with white labels are the borings that we did for this project. The white rectangles with dark lettering are the bore locations that the Bureau of Reclamation did back in 2001. We focused on getting a representative cross-section, so to speak, of the samples in or near the thalweg, and then also distributed out beyond the thalweg on both sides, trying to get a representative indication of the sediment. So this is an actual photo of the sediment in the broken apart sampler tube that was pulled up from the reservoir sediment. This is a graph. This is the percent passing, the sieve sizes that are shown here. You can see in the 6 traces that there was some consistency, but there's also some distribution across it. It was fairly consistent material of silts with some interlaced clay, and then there was also some consistency in how deep the sampler went until we encountered the alluvial material that was the creek bed back before there was a dam. The concrete coring on the upstream face and crest, after the geotechnical drilling operation was over, we actually rented the barge and an operator of this boat, and we used that to support the concrete coring operation. We've got a schedule that shows the locations of the cores and the depths, but there were 4 core holes, 6 inches in diameter and 4 feet deep, drilled into the crest of the dam, and then 1 on the outboard notch on the right side and 1 on the left, and then 4 horizontally into the downstream face of the dam. It was interesting work. They were actually out on the crest, but it isn't as risky as you might think. There was a railing built around the barge that they could work within containment. Yeah, this one shows that actual railing. So that is the crest of the dam, and that's the downstream face, and that's an actual core drilling device going into the crest of the dam. This one is in one of those wings on the upstream face. This shows the core drilling device. It actually gets bolted to the face of the concrete, and then this advances. This is the cylindrical drill that moves into the concrete and pulls a core out. This is a core hole, so that is what it looks like afterward. I'll mention that this was a zero discharge operation, so before this was advanced, there was plastic that was taped around the bottom portion of the core, and the drilling mud was captured so that none of it could enter the reservoir. Core drilling on the downstream face was accomplished with a much smaller, actually fabricated barge that was moved about with a small Zodiac and an outboard. Largely the same drill rig went aboard this raft, and we placed the core holes so it was easily accessible from the elevation of the small barge. This is not actually the drilling operation. This is backfilling the core holes with grout. As part of our permit requirements from DSOD, it was necessary to fill the holes that we drilled back up with grout. If you've ever wondered what a core sample looks like after a hole has been drilled in a concrete dam, these are a few of the samples. Here's one that was more contiguous, that stayed together. There were some that came out as rubble. That's partly because of the condition of the concrete in that section of the dam, but also some of the extraction, especially into those deeper holes. It isn't a perfect operation, so it's tougher to get out. And then there were some that were in between. An array of tests performed on the concrete was done by a lab: compressive strength, tensile strength, modulus elasticity, testing for the alkali-silica reaction that Paul mentioned earlier. Those concrete strength characteristics are used as input into a finite element analysis model that actually has an array of structural and related inputs that go into an ANSYS model, and then provide an output data set that has the stress and strain within each element of the dam. This was modeled with and without the orifices. One of the key considerations is drilling 2 12-foot diameter holes through the dam. Does that compromise the structural integrity of the dam? Under static loading, that is the force of the water and soil behind it, and under dynamic loading, that's an earthquake. And the end result of the analysis is that it does not. There is some objectionable stresses on the left orifice inside the wall that could be addressed locally by lining that section with steel or other measures. But the good news is that the dam will withstand the orifices. There was a study done by URS, which is a predecessor company to AECOM, back in 2013. That study used extrapolated data. They did not do corings to support that study. They used core results from an earlier core drilling session and then just extrapolated the decline in concrete strength from there. But the results of this study with using these cores and this analysis compared very favorably. There was consistency in the results in terms of the stresses and strains across the dam. There was also consistency in terms of the overall structural stability of the dam. It's saying that the dam is structurally stable has to have a date stamp on it. ASR is a progressive anomaly within a dam. It's not quick, but it is nonetheless progressive. And so they were quick to say that the dam in its present state is structurally stable, but we need to keep an eye on it. I mentioned that the small area around the left orifice had some compressive stresses that needed to be addressed. We'll skip right to the bottom line, and this is actually a quote from the report. It's concluded to have adequate safety against overstressing before and after the orifices for assumed static. Again, that's just the water force against the dam, and also dynamic, and that's the earthquake loading. We've obviously, since DSOD oversees dam safety, all things dam safety associated with Matilija, we've been in close contact with DSOD throughout the course of this. They permitted the core drilling. We gave them a work plan before we started, and we're in very frequent contact. We had a meeting, it's coming up on a year ago now, where we presented the preliminary findings of our studies. They have now in their hands a copy of our analysis. They've had it for several months now and are studying the results. They're comparing it to the results of their own study. We use different methodologies, different models. And as soon as they're done, which I anticipate getting a call anytime now, we will meet again and we will talk in more detail about the orifices. We'll talk in more detail about the blasting option. And then also we'll spend some time discussing the structural stability in dynamic loading earthquake. Sediment transport analysis is also a key component, as several folks have alluded to thus far. We know the grain size, we know the composition of the sediment, we know how susceptible it is to erosion, which is what we want. Those smaller particles will move out with enough water force against them. We'll talk more about the flushing flow event in a bit. But the modeling that occurred using that data was in two forms. One was sediment transport analysis. How will that sediment react with water force against it? What will the distribution of sediment look like in the stream bed and river course below it? And then the results of that model, which forms a new profile with what remains of the fine sediment before it leaves completely, and then after the coarser sediment starts to come down as more hydrologic events drive it downriver. So this is a graphic that shows you from upstream to downstream, showing the nodes along the river and divided into A through J is how it was broken up for the course of the study. And we'll just hit in very little detail these next few slides. This is average bed elevation, and this is as it progresses from Matilija Dam in kilometers. What I'd like to point out here is this blue line is how it looks at the dam initially now with that sediment accumulation. And the value that they picked is after an episode of 1,260 CFS. Look at the significant difference in one flow event, how it diminishes the elevation of the sediment. So it is highly mobile, and to no one's surprise. More of the hydraulic analysis. The DREAM2 is the model that is used to model the sediment transport, and then as that establishes what the stream profile looks like, then HEC-RAS is the model that puts the water on top of the sediment, so to speak. The two models are used in tandem. They have some interesting differences. DREAM2 labels the river station from upstream to downstream in kilometers. HEC-RAS labels the river from downstream to upstream in miles, and then they have to find our way to get along. That's just how that ended up working out. Significant differences in deposition upstream and downstream of Robles, downstream of Robles. The deposition of sediment, when the coarse sediment comes along, is much more confined. Upstream of Robles, there's enough sediment that at least for a time it'll find its way adjoining the riverbanks as well. This is a modeled change in the bed elevation and the water surface elevation in the same trace. This isn't what the bed would look like. These are the changes. And here's the zero line. So you'll see the most significant, and this makes sense if you think about it, the most significant changes are up closest to the dam, and the further you progress downstream, the less significant the changes in water surface elevation and bed elevation are. And this is for a future quasi-equilibrium condition. That means long enough after dam removal that the river has achieved a relative balance between sediment that is leaving the system and sediment that is replenishing the system from upstream of the present dam location. This is near the upstream portion of the dam, so again, the most significant change there. So Peter alluded to this, but we needed to understand the correlation and the dependability, the predictability, I guess you could say, of a storm that is forecast and how that forecasted storm will relate to actual rainfall that is received, and then how rainfall that is received will correlate to stream flow, because it's ultimately stream flow we're interested in for that initial sediment flush. Peter alluded to the removing the gates or plugs. Ideally, we'd have 1,700 CFS average over a period of time. We need about 3 days in advance. I've had some interesting discussions with a blasting contractor who would actually do this sort of work. We sort of walked through, he made some diagrams and photos, walked through how that would work with placing explosives in these pre-drilled holes. The science of explosives have come a long way in recent years. Very confident that he could do the job, very doable, but he needs some advance time. So 3 days in advance is what we were looking for. We really wanted to avoid a false positive, and a false positive means that our modeling methodology would tell us that a flushing storm event is coming, but it didn't. We do not want to remove those plugs when we don't have a significant enough flow event to move the bulk of that sediment downstream. So the answer was a multiple regression model. QT-1 is the day before the flushing event. This is the total 3 days before, and then this is the event itself. There were 38, I think, different events that produced sufficient flow, and they were looked at over the years. We had good data on rainfall. We had good data on the prediction of rainfall, the forecast, and then how that correlated. So this is the equation for the line of a linear regression that creates a mathematical statement for how rainfall would translate and be realized as stream flow, in effect. So we had information from 1965 to present. There are just a few peculiarities maybe, or a few interesting things. The daily precip had to exceed 4.5 inches, or total 3-day flow exceeds approximately 8 inches. The equation will predict 1,700 CFS. So those were some precursors. That equation tended to underpredict large flows and overpredict smaller flows. So those flows above 4,000 and 1,000 to 4,000 were adjusted for in the equation by limiting it to this range. Okay. I'll move on real quick. Peter alluded to this a bit, but we're working now on updating the real estate plan. That is how we will address concerns with real estate in the affected area. Would there be flowage easements that are necessary? Will there be protective measures that are necessary? In some cases, would the flood potential be small enough and the potential for damage be slight enough that you would make certain that there are no structures that are harmed, but the damage will be minimal. There are other ways to deal with that. The reevaluation of the project downstream components, he mentioned that as well. The second item is more of the infrastructure that is downstream and studying what measure would be necessary there as well. Short-term and long-term water supply alternatives, working on that now. There are presentations on that today. Short-term is primarily dealing with the reservoir sediment during that initial flush. Longer term is over the longer term when the coarse sediment starts progressing down the river. And then dam removal plans to 10% or conceptual level, providing some drawings and a description of how this dam removal sequence would work, including the construction of the tunnels coming along as well.